Let us begin in the name of our Lord. Maxwell's equations in differential form. Consider a charged particle Q. Let Q denote a charged particle. E denote electric field. B denote magnetic field. If we draw a curve, a line or a curve that goes from Q to E, it tells us that a charged particle is a source of electric field. Where there is a charged particle, there is an electric field around it. Now, that is okay and it's true not only for stationary charges but for moving charges. That means even moving charges also produce electric field. Of course, with a difference, but we are not bothered about that difference right at this stage. What we mean is electric field has a source, at least one source, that is a charged particle. Then if we draw an arrow back, we have then, it tells us that if there is an electric field and you place a charged particle at any point in that electric field will influence that charged particle, will exert a force on that charged particle, and that force is equal to QE. QE, that is the force. F is equal to QE. Force exerted by an electric field on a charged particle. Similarly, if you have a charged particle, moving charged particle, this time it is moving charged particle, it produces an magnetic field. And a moving and a magnetic field has influence on a moving charged particle, not stationary. Now, this force exerted by a magnetic field on a moving charged particle is given by F is equal to Q V cross B, and is called Lorentz force, Lorentz magnetic force. The two forces together are called Lorentz force. And then there is another law, that is a changing magnetic electric field. A changing electric field is associated with a magnetic field, and a changing magnetic field is associated with an electric field. That completes at least those laws of electromagnetism which are expressed by the beautiful Maxwell's equations. Although the equations were not derived in the form that we know, they were not derived by Maxwell, they were rather put in that form by Heaviside and Hertz, yet the equations have been named in his name to honor that great person. Now, this QEB triangle summarizes our laws of electromagnetism. Okay, we will now like to express them mathematically, because until you are able to express things in mathematical language, you are not sure about their utility, about their importance. Mathematics is the language of nature, and so let us go for that. First of all, we will take up the first law, the Gauss's law. Gauss's law of electromagnetism. Gauss's law. See, Gauss's law tells us simply that electric flux through a closed surface, S is electric flux through a closed surface, is equal to charge enclosed by that surface divided by epsilon naught, which serves as a constant of proportionality, 1 by epsilon naught. Okay. Looking at this equation, you have to do one thing. You have to forget about this forget about this and see what is left. You are left with E. And then this equation tells us E, electric field, is due to this charge. That means behind this dazzle, you have to recognize the most important aspect of an equation. The most important thing about this equation is that it tells us that electric field is due to a charged particle, due to a charge, electric charge. Now, why do we express it like this? Yes, let us see. Suppose you have a charged particle Q, and then it is electric field, electric flux, and so on. You have a closed surface S. You want to calculate what is electric flux through this surface. Okay. Now what you do, you divide this surface, the area of the surface, into little areas, area elements. Let us show one such element here. Although it appears like this straight line, it is not a straight line. It is a straight plane page of area. Now this area page is, suppose it has an area dA. What is the orientation of this area? This is the orientation of this, denoted by its normal, outward normal. And this is electric field. And when you calculate dot product between electric field and dA, dot product between them, you will get E dot dA equal to EdA cos 0 degree. Now cos 0 degree is 1 plus 1. So you will get a positive quantity. This is positive, area is positive, this will be a positive quantity. So flux here will be positive. Electric flux here will be positive. So will be positive here. So also here. Because again, normal is outward, electric field is outward, angle between the two is 0. The same thing is true for all other points on this surface. When we add up these individual fluxes to get the overall flux, we get a positive flux through this surface. That means there is a net flux through this surface, and this net flux is due to the net charge enclosed by this. Now to test this, whether it is true what I said, first of all, let me not enclose any charge there. Let the electric field come from a charge that is outside, not inside this. So there is no net charge now inside this. So what is flux through this? Well, you will see here electric field line is going out. Flux will be positive. Simply because if you take an area element, its normal will be this normal, this will be electric field, and this angle will be an acute angle. Cos theta will be positive. So is the case everywhere here where it leaves the surface. But where it enters the surface, suppose electric field line enters the surface, say there is dA, and this is normal of this dA, normal, okay, outward normal, and this is electric field line, and angle between the two, it is not, you can see, or angle between the two, the smaller angle between the two, that is obtuse. So electric flux here will be negative. The same is the case here. That means that these lines have the property that they enter at one point and leave at the other point. While they enter, they contribute negative flux. Where they leave, they contribute positive flux. Here, the situation was different. All lines were simply leaving, not entering anywhere. So we won't get any net flux here. Positive fluxes will be cancelled by negative fluxes. Hence, there will be no electric flux through this closed surface. Good. Then, suppose now, the reason we saw there is no net charge inside it. Suppose there is charge inside. but there are equal and opposite charges. A dipole. There's a dipole. Now, what is the flux through this closed surface now? Now, see, a dipole magnetic electric field line of this dipole is one electric field line. It's like this. This line, it leaves here, therefore contributes positive flux. But the same line, when it enters here, contributes negative flux. The total flux contributed by this is 0. Same is the case with other dipole lines. So what we conclude? We conclude that there is a net flux through any closed surface only when the surface encloses a net charge. If there is no net charge, no flux is there. And the greater the charge enclosed, the greater will be the flux. Why? You can just see it here. Suppose instead of Q, we had 2Q. So suppose this produces 1, 2, 3, 4, 5, 6 lines. This will produce 12 lines. So its lines will be more crowded. More crowded means you will get more flux as compared to this. Hence, we conclude that electric flux through a closed surface is directly proportional to net charge enclosed by the surface. And if we introduce a constant of proportionality, it comes out to be, which you can easily test yourself, comes out to be Q enclosed divided by 1 by epsilon naught for a surface and a charge in free space. Now, this is what we call enclosed. This is the closed surface. This is, say, it is not necessary that charge be localized at one point. Charge can be spread out in the volume. And then, suppose we have total charge inside this surface, that is Q, and then enclosed by the surface is Q. And this charge, so imagine this charge to be divided into infinitesimally small elements of charge, each of dq magnitude. Then we can write it integral E dot dA is equal to integral dq by epsilon naught. But integral dq, that's our volume. Now then again we can write this dq as dq by dV, that is volume charge density, rho. Therefore dq can be written as rho dV. Therefore we have integral E dot dA is equal to integral volume integral dq, in place of dq you have rho dV by epsilon naught. We now use Gauss's theorem. Please remember that we have curve, then surface, then volume. When we go from this to this, we use Stokes' theorem. Or it is reverse, it is converse, Stokes' theorem. When we go from this to this, that is Gauss's theorem. Whether this is Gauss' theorem or Stokes' theorem can be easily decided by just recalling that Gauss's law is about flux on one side and charge on another side. That is, Gauss' law is basically a surface to volume relation. Surface to volume relation. Okay, anyhow, we want to convert this surface integral into volume integral. And we know that we have this theorem that if you have a surface integral of, say, electric field over a closed surface, then you have, suppose this is closed surface, then this is equal to volume integral of its divergence del dot E dV. This volume integral of its divergence of this. That is, flux of something is equal to divergence of that thing. divergence. Now, applying this to the left side of the equation of this equation, we get integral v volume integral this del dot e dv is equal to integral v rho dv by epsilon naught. We can cancel these integrals and dv's, and we will get del dot e is equal to rho by epsilon naught. Now, you can cancel these because this equation is true for all volumes. What does that mean? That means if you have a charged particle here, and suppose you have a charge, a continuous distribution of charge here, and then suppose you apply this Gauss's law to the entire volume. It is true. You apply to half of the volume. Again, it is true. Apply Gauss law to any this portion of volume. It is true. That means Gauss law is true at every point. So if it is true at every point, then these must be equal at all points. For every point they must be equal. Therefore, del dot E is equal to this. This is called Gauss's equation in differential form, or also called Maxwell's first equation. This is volume charge density. Now let us go to Gauss's law for magnetism. For magnetism, it is quite simple. For magnetism, flux is always zero. Flux through a closed surface is always zero. So it yields us zero. What I mean is this. When you write here flux, electric flux, you write charge enclosed on this side. Charge enclosed on this side. Now, in case of magnetism, you will have magnetic flux B dot dA is equal to charge, magnetic charge. So magnetic monopoles do not exist, even though it is really a puzzle, but it is an experimental fact till now that we have not been able to detect them. So if these poles do not exist, magnetism occurs only for us. Magnetism occurs only in this form. Suppose you have the simplest form of magnetism is a dipole. North pole, south pole is a magnet. North pole, south pole, and this dipole. Suppose you enclose a closed surface around it and then calculate its magnetism. What is the net magnetism enclosed by this? That is zero, because this magnetism and this magnetism, they are opposite. Now, this also can be understood by this fact that when a north pole leaves from this, it turns to this. Again, it contributes positively here, negatively here. Overall contribution is zero. So we have this magnetic flux through a closed surface equals zero. This is Maxwell's second equation in differential form. Now we have next Maxwell's third equation. Maxwell's third equation is basically relation between E and B. What is that? What does that mean? You have studied rather, that suppose we have a closed loop, conducting loop. Let this be a conducting loop. Okay. Do we expect any current through it? No, there's no source of current, so no current is expected. But see, suppose you have again conducting loop, but with one difference. And that difference is, suppose you have a conducting loop with a, say, this is conducting loop with a cell connected like this, positive, negative, connect like this. Do we have current in it? Yes, definitely. Electrons from the negative terminal of the battery, they flow towards positive terminal and there results a current. But there is one interesting thing about this current, that is When electrons go from negative, they rush away from negative because they have high potential here. Electrons have high potential as compared to electrons. An electron in the company of many other electrons has high potential energy. We say that it is high potential here, and it rushes away from high potential to lower potential here. It's a sort of hell for the electron, and when this electron reaches here, it finds itself in heaven. But then, that's not the whole story. If this would have been whole story, that electrons leave negative terminal and reach positive terminal, then this negative potential would fall quickly. Positive potential would also fall quickly because the electrons that would arrive here would neutralize this positive charge there. So there would have been, after a moment, there would have been no current at all. But we know, we are well aware of steady currents that persist for many days even. Now, what happens is this, that look at a particular electron, when this electron goes from higher potential to lower potential, it is transported from lower potential to higher potential by this cell, and that is the essence of the source. That means a source of electric current basically has a capacity that it transports charge carriers from lower potential to higher potential. Of course, against their will, against what they would like. But this means that this cell does work on charge carriers. Yes, it's something like this. If you have, suppose you have a small pebble, you have a pebble or anything in your hand, you let it drop, it will drop of its own. It does not need your push. You just release it, it will drop because of gravity. Now, but once it is here, it will not go back of its own. You need to lift it. So you need to do work. You are taking it from lower potential to higher potential. Who would like to go from heaven to hell? Well, if there is compulsion, then, well, that compelling agent must be doing work. This work that is done by the source of electric current is known as EMF. Therefore, we write EMF is work done per unit charge in transporting that charge through a complete circle in a circuit. That means we start with the charge at one point, say this negative terminal, and then bringing that charge back to negative terminal needs work to be done. And this work per unit charge is called EMF of the source. EMF is property of sources, not passive conductors or insulators. Now we can write work, therefore we can write EMF is equal to work done. For work done, since work is being done in a loop, in a closed loop, and we can write it as loop, let us, we denote loop by gamma, and then this loop is closed, and we will write it force into work, force into displacement, that is F dot dl divided by Q, and force, if it is electric force, then electric force is work is done by electric force. Now against electric force, either it should be electric force or done by against electric force. Since the work here is being done against electric force, so we can write F is equal to E is equal to Q F by Q. That gives us F is equal to QE. And when we substitute it here, we have EMF is equal to integral, loop integral QE dot dl divided by Q. That gives us integral E dot dl. Just keep this thing in mind and let us move add. Now, what Michael Faraday, the great natural, I should say, natural scientist or a natural physicist and chemist, that he discovered, one of his greatest discoveries was that when there is a closed loop without any source connected in it, no one expects that there will be any EMF. So there is any source of EMF in it, and EMF is needed for EMF. Of course, is needed if you want a current in it. Then EMF is needed. Now there is no source of EMF, so no current is expected. But when you bring a magnet, and that magnet produces magnetic flux, some of which links with this coil or passes through the coil, and if this flux through the coil, through this conducting loop changes, an EMF appears here. How do we know? We find a current, and this current can be easily detected by galvanometer. This great discovery, which is the basis, which forms the basis of many great technological innovations. This great discovery is reflected as or described as EMF. There is an EMF induced in this circuit, which is directly proportional to rate of change of magnetic flux through it. Magnetic flux. This magnetic flux here. Magnetic flux. Electric flux does not do it. Now, good. Now, we can now write for EMF, induced EMF, we can write integral, just you saw it, EMF can be described as line integral E dot dl, E dot dl, E dot dl is equal to minus d by dt b, phi flux, that is b dot dA. Integral b dot dA, but surface integral. This is the definition of flux. Surface integral b dot dA. Just as we have E dot dA in case of electric flux, we have b dot dA in case of magnetic flux. This is magnetic flux. Okay. Now we can do one thing now. We can first of all, let me do this thing. I will write therefore integral E dot dl is equal to minus integral dB by dt dot dA. Okay, now then this is surface integral. Now next, we now convert. We now use Stokes theorem. Why Stokes theorem? Because you have loop integral here. And what does Stokes theorem tell us? Stokes theorem tells us that loop integral, just to remind you that loop integral of magnetic field, we derived it for magnetic field. Loop integral around a closed loop is equal to volume integral. Surface. It is surface integral of curl. Surface integral of its curl. Surface integral of its curl dot A dot A. This is Stokes theorem that we studied, that derived in that particular lecture. Now, using this for electric field, we have just for this electric field, we can write here, replace B by E, and not only replace B by E, but also replace this whole side by this surface integral. So I will have surface integral of del cross E dot dA is equal to this minus integral dB by dt dot dA. Now since again This must be true for all types of surface, whether small or large. Therefore, we can simply write down from this, we can simply write down del cross E, del cross E is equal to minus del B by del T, minus del B by del T. This is what we call Maxwell's third equation. It is also a differential form of Faraday's law of electromagnetic inductance. Okay, that we are left now with one equation, the last equation. It all starts from this thing that if you have suppose you have a wire like this going up. This wire is going up towards the reader with current towards the reader. Okay, steady current. Current is steady. And then what we do, we calculate its circulation around this loop. This is a loop. We calculate its circulation. Well, we find that this circulation is B dot dl is equal to mu naught I. This is Ampere's law. We are well familiar with it. It simply says us that magnetic field, where there is current, there is magnetic field. Okay, then you have this loop integral. Okay, now we can express this current in terms of current density. What is that current density? Let us see. Suppose you have a wire like this, and then current is flowing in this fashion. For the moment, let the current be steady, constant, does not change with time or space. Then we can write current, if we divide this current by the area through which it flows. Area of cross section is to be taken as constant everywhere. Then if we divide this current by area through which it flows, we call it current density. So simple. But look at the current and the area of cross section. In this definition, one thing that is assumed implicitly is that current is oriented perpendicular to the area of cross section. What does that mean? That simply means, suppose we had this type of current, this area of cross section, and we did not have this type of current there. We had this type of current that goes parallel to the area of cross section. It runs parallel to the area of cross section. We say there is no current density across this, through this. There is no current through this. Of course, that's true. So only though that component of current density contributes, which is perpendicular to this. It is like flux. That means if you have a area of cross section like this and current density in this direction, let this be the direction of J, current density in this direction, then not all J contributes to the current through this surface, through this area of cross section. Only that component, only for example out of this, only this component contributes, only this component, only the perpendicular components, they contribute. The greater, see, the greater the, now one more thing, that is, suppose you have an area of cross section like this. What is this area of cross section? Held perpendicular to the plane of the screen. Now, if I ask you, what is the direction of this area of cross section? You will simply say dA. This is the direction. Say dA. Direction. Why? Because all surfaces are oriented in their normal directions. Normal, whatever direction that normal has at a point. Okay. Now, where is the normal here? It is this. This is the normal. This is the area, direction of area. This. Now, question is, if J is more and more parallel to dA, you will get more current. If J is less and less parallel to DA, this is DA, you will get less current. In fact, here you get zero current. Now see, if the angle between J and DA is 90 degree, then current through this surface is zero. If the angle between J, this is J, and this is A, DA, okay. If the angle is zero, then current is maximum. If the angle is somewhere between 0 and 90, current is neither 0 nor maximum. This means this relation between I and J is like that of dot product J and dA is like that of a dot product. Oh, definitely. That's why more general definition of this would be, see, instead of writing I is equal to J, we write I is equal to J dot A. For a small area element, J dot A, let us write DI, J dot DA. Instead of J into A, J dot DA. Now, if the two happen to be parallel, well, that is J DA, the same as this. If they happen to be perpendicular, then it is 0. A total current is calculated simply by an integral of this J dot DA, but see which integral it is. Since you are dividing area of cross section. The integral that you are taking is a surface integral. So I think this must be clear to you. Now we can write I is equal to integral J dot dA. Next, this surface integral. Now you know this surface integral. Suppose I want to convert it into this volume integral. How can I do that? Quite easy. That can be done easily by using, since you are going from surface to volume, you will have to use Gauss's theorem. If you would like to convert it into a line integral, then you will use Stokes' theorem. Okay, let us see what let's see at which type of this conversion we would like. Let us move. We can now write, now you have here this Ampere's law, that is, this is the loop, and conductor is going up. Now if conductor is going up, J is up, current is going up, J is up, okay. dA, that means the surface through which this current passes, that surface is this, through which this current passes, that is this. It is piercing through this surface upward, just as it was here. Current passing through this perpendicular to this. This current is passing perpendicular to this. Well, then we write magnetic field, circulation of magnetic field is equal to loop integral of magnetic field is equal to mu naught I. Now, but suppose if the wire is not held like this, if the same wire is held like this, it does not contribute any. It is only the enclosed current enclosed by this loop, or current threading through the area enclosed by this loop, not the current that runs parallel to this surface. Why not this current? Simply because it contributes overall circulation. Its contribution to overall circulation is 0. Why it is 0? That is okay. Let us see. If you take this point here, say some point, and then find the direction of magnetic field due to this wire here. You can use your right hand rule and you will find that magnetic field here, it is, or you can use Biot-Savart's law, dl cross R, whatever you like, you will find one thing, that is magnetic field goes down into the plane of the paper. Here it is down into the plane of, and here it will be up. Sorry, I'm showing it wrongly. It is crossed going into the plane of paper, coming up out of the plane of paper. And when you would calculate contribution of this magnetic field to the circulation, it will be 0 because magnetic field is downward. dl is this way, dl is this. magnetic field is downward, angle is 90 degree. So no cos 0 degrees, cos 90 degrees 0. Same is the case with these. So that means this is not the whole current, any current. No, this current, which there must be either this current or a current that has at least one vertical component here. The same thing can be expressed better by this equation then. B dot dl is, you see mu naught j dot dA. Mu naught j dot, we can write current always as you saw it here. Surface integral of j dot dA. Now, if we convert this into surface integral, let us do it. Let us convert it into surface integral using a Stokes theorem. We have, according to Stokes theorem, B dot dA dl is equal to, this loop integral is equal to surface integral of curl of B, curl of B curl of B and surface integral of curl of B dot dA. Because it is surface integral, so we will have a dA here. Now if I replace this by this side, then I get del cross B is equal to del cross B dot dA is equal to, that is equal to mu naught, this dA, for this mu naught integral j dot dA, and we can then cancel out these. This is now surface integral, and we can cancel out this, and we get del cross B is equal to mu naught J. This is Ampere's law in differential form. What Maxwell discovered was that there is a mathematical discrepancy, inconsistency associated with this. How? Suppose you take curl or this divergence of these two sides, del cross B is equal to mu naught del dot G. Okay, good. Now we know that this must be 0, because simply if you have A dot A cross B, the direction of A cross B is perpendicular to A, and then when you take it as dot product with A itself, since it is perpendicular to A, theta is 90 degree and cos 90 degree is 0, so this is 0. This must be 0 equal to mu naught, but there is no guarantee that del dot J will be 0. It can be 0. Divergence of this current density can be 0. For example, here, if you have a uniform cross section, this a conductor with uniform cross section, and you have current flowing like this, of course, it doesn't diverge. You see, there is no divergence. On the other hand, if you have something like this, then you have, you see, yes, now is the divergence. There is divergence, a negative divergence, or you could better show this of larger area of cross section. Then the lines, these current density lines, would run away from each other, and there is a divergence. In short, what I want to convey is that there is no guarantee that divergence of this is zero. That means there is a mathematical problem. How to resolve this? There must be something wrong with this equation itself. How to resolve that? There is a way. One way is, you see, you have del cross B equal to mu naught J, okay, you have this. And then if you want that divergence of both sides must vanish, then this is one thing. And always this divergence of this always vanishes. Del cross divergence of a curl is always zero. Mu naught del dot J. Then there is a way to, till this stage, the equation is wrong. But if we do one thing, if we add another term here, a negative term equal to this, and write del dot del cross B is equal to mu naught del dot J minus mu naught del dot J. Well, you would say, sir, this is simply that you are arranging things. Now, you have this minus this. Definitely that will be zero. This is always zero, so this will be zero. But then, what is most striking, that is, Maxewell had this idea that del dot J can also be expressed in another way. So we can write del cross B is equal to mu naught J minus mu naught J. Of course, this side will be zero. And if it is zero, then taking curl of this, taking divergence of this, and taking divergence of this will always satisfy this equation. But this term that Maxwell inserted in this Ampere's law, this term can be given another expression. That expression is very, very important. What that is? First, let us see. If we have something like del, let's take first again divergence of this equation throughout, divergence of this equation, that is mu naught del dot J minus mu naught del dot J. Okay. Now you know this del dot J, that is divergence of current density, can be expressed in another form by using equation of continuity. Now, maybe some students among you might not be familiar with that, so it is not difficult. It is so simple. You have a surface that encloses a volume, and that volume encloses charge. This electric charge enclosed by this volume. Total charge is Q. Now, if this charge is moving through the surface, it computes a current. There is current through this surface. This current can be written as dq by dt. Now, but you know, I can be replaced by integral j dot dA, where J is current density, and this is S closed surface, and this is dq by dt, with one coefficient, of course, that is, I will write minus here, because this charge is actually decreasing with time because charge is leaving out. This equation is called continuity equation. This can be expressed in another way. We can convert this by using Stokes theorem. We can convert it into volume, this integral, that is V, and then replacing del dot J dot into dV is equal to minus d by dt. So far as this charge is concerned, I can write rho dV. Now you can, rho dV, volume integral, and dV. Okay. Now you can cancel these, and you will have del dot J equal to minus rho. Okay. But as far as rho is concerned, we have to, it is d rho by del rho by del t. As far as rho is concerned, we can discontinue the equation. No, as far as rho is concerned, we can use Gauss's law for this. We have Gauss law, del dot E in differential form. Del dot E is equal to rho by epsilon naught. By cross multiplication, you can write then del dot J is equal to minus d del by del t, rho del dot E. So let us do one thing. Let us substitute this in place of this del dot J. Let us substitute this quantity there. We have, if we do that and keep this del dot J as it is, now we have del dot del cross B is equal to mu naught del dot J plus, now plus, why? Because you have minus here and you have minus here. You have minus here, here you have minus, and this whole term comes out to be this minus. So you have plus finally, that is del by del t, mu naught first, this mu naught, and del by del t, del dot E. Now cancelling out this divergence, we are left with del cross B is equal to mu naught J plus mu naught epsilon naught it is E, epsilon naught E, but d by dt E, electric field. That gives us finally del cross B is equal to mu naught J plus mu naught epsilon naught del E by del T. This final equation does not have that flaw which Ampere's law alone would have. Now, this additional term is known as Maxwell's displacement current, and this additional term has something really beautiful for us to know. That is, it tells us that, well, this magnetic field has have two sources. One source is current. This is current, steady current, constant current. And other source of magnetic field is a changing electric field. In Faraday's law, we found that curl of electric field is equal to minus del B by del T. This Faraday's law tells us that electric field has a source that is a changing magnetic field. It means that wherever you find a magnetic field changing with time, you will find an electric field around it. That means we say that a changing magnetic field is associated with an electric field. This equation, this Maxwell's correction, actually, it restored symmetry in physics. There is complete symmetry now. You have a changing magnetic field associated with an electric field. You now have changing electric field associated with a magnetic field. And as we will study, if God wills, we will study and we will see consequences of these equations about whom someone said, has God written these equations? So these are Maxwell's four equations. This is the fourth, this is third, this is second, del dot B, and this is that is 0, and this is the first, del dot E, that is rho by epsilon naught. We will study their consequences now, but first we will take up conservation laws. Thank you.